In this video, I will be observing buffer distribution across packet forwarding engines and latency on Juniper QFX10K switches. So QFX10K is a virtual output queue switch, which means that there is no output queue as such. Output queue on egress port is represented with this entity here that we call virtual output queue, and each ingress packet forwarding engine, depending on the traffic that is sending in that particular queue, will have a virtual output queue created on it with certain resources that are going to be reserved. Buffering on QFX10K, as we can find out from our documentation, happens only on ingress PFEs. Egress PFE plays no role in buffering. Also, we are used to think about buffer space in terms of latency, and the two variables are very closely connected. They're very tightly coupled together. So in this particular example, we will be observing latency and then try to make conclusions about buffer distribution across PFEs, because latency is something that we can measure using a test generator. And here we are used to thinking of 100 milliseconds of available buffer per port. And usually that means egress port. But we need to be aware of the fact that this 100 milliseconds is going to be distributed across ingress PFEs. So I will be observing only one queue, and I have allocated certain buffer space for it, like 30%. That 30%, under the congestion, when only this queue has traffic, no other queues, I would expect that this 30% out of 100 milliseconds translates into a latency of 30 milliseconds. So under the congestion, when I have only one flow and only one queue and using only one packet forwarding engine, I would expect pretty much that I get 30 milliseconds of delay. Also, there is a little asterisk here, which means that 100 milliseconds per port, but not, and this example I'm not going to look at, uh, not if every port on packet forwarding engine is under congestion at the same time, it cannot get 100 milliseconds. So there are more ports than there is a memory per packet forwarding engine. So this is not meant to be each port on the same PFE congested at the same time. So then this number doesn't hold anymore. But this is the case that I'm not observing. Also, how this 30% or 30 milliseconds translate in terms of bytes. So the calculation is super simple, and this gives us actually the number of memory that is going to be allocated for buffer. So let's start with, I will be using QFX10K, QFX10K2 actually. XCI is a test generator, and we are going to send, for the first case, we are going to send one flow and observe what happens in this case, whether we can get to these 30 milliseconds and whether XCI agrees actually with our assumption that 30 milliseconds should be the delay in this case when this port is under congestion. I can offload with 40 gigabits per second, and I can offer rate of 100 gig of seconds, bits per second. So let's get to Ixia, and for starters, I'm going to look into this particular queue. Before I start traffic, I just want to see that all counters are clear. And here we are going to monitor egress port. And here I'm slightly oversubscribing the egress port by sending a rate, because my ingress port is 100 gig, I'm sending like 40.1. Idea being, I just want to see how latency starts to creep up and how the buffer starts to fill up. So kind of just to show actually. So let's see, latency is already creeping up. And at some point, I should see drops. And sure enough, I can see drops, and I see that this number basically stopped at 29.9 milliseconds. So now if we go back to our slide, this number is very close to 30, because we said we should expect 30 milliseconds of delay. And sure enough, Ixia agrees and says that it's around 30 milliseconds. We are in that ballpark, so far everything is good. But let's check actually what happens on the packet forwarding engine. So for that, as I said before, again, I'm interested on egress packet forwarding engine because this is where buffer is going to be distributed. And in this particular case, when I have only one flow and only one packet forwarding engine, I know that complete buffer needs to live on packet forwarding, this particular packet forwarding engine where this port lives. And it happens that this port of interest is on packet forwarding engine 0. So let me start shell here. See, if I quickly want to see actually the mapping of ports and PFEs, there is a nice command to show me that. So our port 0043, I can see that lives on packet forwarding engine 0. Then I want to find index of the port that is egress port. Because again, when we apply schedulers, we are applying schedulers on the ingress port. And my ingress port is this one, ET001. So show IFD brief. And ET001 has this particular index. So 660. And here I can check how the packet forwarding engine is programmed. The queue of interest here is this one with 30% of buffer percent. This is queue number 2. Other parameters of this queue are not important for my example. But what is important is actually this value. So each queue, in this case queue number 2, will have a particular virtual output queue number. That number is here. And we are now going to look for that number on ingress packet forwarding engine and see what data ingress packet forwarding engine is going to give us for this particular virtual output queue. So and here I can see that I have a parameter called queue length. Get ingress queue length for this particular virtual output queue. And why this queue length is important? Because in this particular case, as I'm congesting this port, I expect that the queue be fully utilized. And then I will be able to relate that value with the buffer size that we have allocated for this queue. So queue length, and then it's asking me on which PFE. I know that my port lives on packet forwarding engine 0. So this particular port, ingress port, lives on packet forwarding 0. So I would say chip, And let's see these interesting numbers. So current queue length, so this is now what is the number of bytes that packets are using to be stored as the queue is under congestion. And we see that this number is, perhaps it's better to find it here, is 4142 megabytes. This number is very, very close, because this is now again what packet forwarding engine is telling us. So current queue utilization, this number is very close to 150 megabytes, because our expectation is that the whole buffer is now on the packet forwarding engine because I have only one flow. And pretty much I think packet forwarding engine agrees with that. But interesting point is that it's giving us here a drain rate. And it says your drain rate, current drain rate of ingress PFE is 40 gig. So let's now use calculator and quickly assess how much time would it take to drain this queue with this rate and with this number of megabytes of buffer used. So I'm going to copy this number times time by 8 because I need to go into bits, and divide by this value, multiplied by 1000 because these are seconds. I want to go into I want to move that into milliseconds, and we see that delay necessary to offload, to drain this buffer with this current number of bytes in the queue, not with the number of bytes in the queue, with the number of packets in the queue that have expanded the queue up to 142, is 28.9 milliseconds. If we go back and look at Ixia, Ixia is telling us it's around 29 milliseconds. So we are here in the ballpark. So 30 milliseconds, Ixia says 29.9, around 30 milliseconds. And our packet forwarding engine is also saying that it can offload this queue pretty much in 30 milliseconds with this particular rate. So let's put these values on the diagram and make some conclusions here. So we know that we are offloading with 40 gigabits per second. 40 gigabits per second I have on my egress port, but the drain rate of ingress PFE is also in this case 40 gigabits per second, and the current maximum latency is 29.9 milliseconds. So that all agrees. That all agrees, and this looks good basically. So let's now add another flow through another ingress PFE and see what happens. So this port, ingress port, lives on packet forwarding engine 1. It is also a 100 gigabit port, and I'm going to start with a similar line rate of 40%. So it's 100 gig port. I'm going to send again like 40 gig of traffic. And let's see what happens in this case. I'm going to also clear all statistics because we want to observe this under the steady state. So waiting for statistics to be cleared. And we have here a situation that maximum latency in this case is, it says around 32.7. So the latency has gone up a little bit. And let's see now what happens. What is packet forwarding engine is telling us for this particular case. So under these circumstances where I have now two flows going through two different packet forwarding engines, I see actually that the queue almost halved. So that means this is telling me that the buffer size shrinked per packet forwarding engine. So previously, if we remember, Q was able to expand to this value, but now it's almost half of that value, roughly half. And also interesting point to say here is that drain rate is 20 gig, around 20 gig. So we see that buffer size halved than it was before, and the drain rate is also now dropped from 40 gig to 20 gig. Previously, if you remember, was 40 gig, and this was the buffer size. Sorry, I sometimes say buffer size and queue length. No, this is just representation of buffer size through means of the size of the queue. So here it's 20 gig, and the queue length shrinked to 77 meg. So in this particular case, if we observe, if we go back, uh, by the way, we see that this 77 is kind of half of this 150 megabytes, roughly. So what we see that latency has gone up slightly, but the interesting point here is that these two packet forwarding engines, ingress, are offloading traffic with 20 gigabits per second. So now this leads us to the important point when it comes to QFX10K. And there is a rule which says each ingress packet forwarding engine is treated equally and given equal share of bandwidth by the egress scheduler. This is done in work conservative manner, which again means ingress PFE is given bandwidth only if it has traffic to send. So it means it's deficit round robin. So it doesn't give actually equal share of bandwidth, but then that PFE idle. So PFE will always use only up to the point to drain the traffic. So that is meant by work conservative manner. Okay, so let us now add a third packet forwarding engine and the flow of 10 gigabits per second. So this situation now is interesting because my ingress speed is going to be 10 gigabits per second. Flow will also go through another ingress PFE. And let's see what happens in this case. So this port, here's my 10 gig port. I'm sending 100% of line rate. And again, I want to observe this in steady state. So I'm going to clear all statistics. And his first observation here is that, let me clear statistics one more time. But first observation that I can see here, the latency on these two has creeped up a little bit, but it's kind of equal because the rate of offer rate is the same. But look at this latency. It's just not comparable to the latency of above flows. It's like 1,000, even more than 1,000 times smaller. So this is like 0.1 millisecond. Let us put that on the diagram. So what happens in this case? How actually, what are the drain speed of these egress PFEs now? And if we go back again to that each ingress PFE is treated equally and given equal share on bandwidth by the egress scheduler, what that means is that if I have three packet forwarding engines, then their equal share is 40 divided by 3. And that is like 13.3. But because it's a work conservative manner how they offload traffic, that means this one will get 10 gig because 10 gig is less than 13.3. And it's actually bandwidth will be allocated to upper two shared. Leftover from this one will be shared because they're out of profile, and this one is using actually less than it's entitled to. So let us check. So now our assumption now is that this one is draining with 10 gigabits a second. It's offering 10 gig, but it's also draining of 10 gig. And because of this equal share of bandwidth, they're all entitled to maximum of 13.3 of 13.3. And because this one is less than 13.3 and it's a very conservative manner, its leftover bandwidth will be allocated to upper two PFEs. So let's go to PFE again. And if this, let me go back. So this is packet forwarding engine 4. So here I'm going to check what's happening now for this particular flow of 10 gigabits per second. And I see that current queue length. So this queue is almost not utilized at all. It's just super small. And even it says here queue length too small to compute drain rate. But we know the drain rate is about 10 gig per second. That leaves us with 10 gig for this one. And if our mathematics is correct, these two packet forwarding engines will get 15 gigabits per second. Again, let us quickly check previous queues on packet forwarding engine 0. We see again that buffer has shrunk. It's only 60 megabytes. Actually, buffer shrunk because we know that queue length shrunk. So that is how we know that buffer is now distributed across 3 packet forwarding engines. And we would expect like to be like 50 meg, 150 divided by 3, but it's 60. So how packet forwarding engine, by which algorithm, and these are discrete values, so it takes some discrete values. And so this is how it allocates in this case. Also, the offloading rate is what we suspected. It's 15 gig. Again, it's 15 gig. And if we quickly, again, take these numbers, just to check them, to check our logic, if it's okay, times 8 divided by drain rate times to get milliseconds, we get 32.2. And what does Ixia say? Ixia say, yeah, 33.7. So our mathematics is okay, is correct. Everything seems to be in agreement. Obviously, because the third flow that is going through packet forwarding engine that is not oversubscribing, that is, how to say, it's in profile in terms of this value here. Obviously, that Q is going to be close to 0. No need to use the Q from that one. And we see that switch is able to hold the latency of around 30 milliseconds under these conditions. Just for something to think about, there is a particular command that, so what we concluded here is basically that buffer is divided equally among packet forwarding engines. There is a particular command actually that is, this is still work in progress, as I understand. And for example, look what happens now if I disable packet forwarding engine averaging of the buffer on the packet forwarding engine. So at the moment, default value is enable. So it is saying uh, average buffer across PFEs. But if I disable this, let's see what happens now. The latency has just gone up. And if we go back and look now at distribution of values per packet forwarding engine, I can see that I have pretty much now the full buffer space that I had previously that was divided among three packet forwarding engines. It's now distributed per PFE. So what I'm saying here, don't shrink the buffer per PFE. Give me the same, if I said here 150 meg, if I said here, give me 150 meg on each ingress packet forwarding engine. And, and because of that, the latency has gone up. It has gone up because now buffer is much bigger and the drain rate actually is the same. So we see that the drain rate is 15 gig, buffer is now 150 meg per second, and the latency has gone up. Also, another interesting command is that I can say keep the latency basically in check. And let's see if we put like some number of 25. So let's see now what happens. I'm clearing the statistics so that I can get, and look at this now. The latency has gone down. So with previous command, I say average packet latency keep no more than 25 milliseconds. So whatever you do with the buffers and drain rate and everything, keep the latency in check. And now the system is trying to keep this latency in check. So basically, obviously it's not equal, but it's trying to get all the values, buffers and drain rate in a way to get this latency down. So I hope this video was useful and thanks for watching.